Hi everyone, welcome to 8th class of electrostatic potential and capacitance. In the previous lesson, we discussed parallel plate capacitor. We derived the equation for capacitance of a parallel plate capacitor. What was the equation for capacitance of a parallel plate capacitor? C is equal to epsilon 0 A by D. Today we will discuss the effect of introducing a dielectric medium between the plates of the capacitor. We will discuss the effect of introducing a dielectric material between the plates of a parallel plate capacitor. So first we know the equation for the capacitance of a parallel plate capacitor with the air between its plates. Recollect the equation. Last class we learned, let it be C0 epsilon 0 A by D. Now this is the parallel plate capacitor, and we are keeping a dielectric slab fully between its plates. Okay, so feel positive charge on this plate, negative here. You know, this will induce an electric field in the dielectric. So now electric field between the plates we can write as E as sigma minus sigma P by epsilon 0. Okay, when there were no dielectric medium, it was E0 was sigma by epsilon 0. When you introduced dielectric between the plates, the dielectric is polarized. Sigma P is the charge density due to polarization. Sigma was the charge density between the plates. So effective charge density is sigma minus sigma P. So electric field is sigma minus sigma P by epsilon 0. And for linear dielectric, sigma minus sigma P equals sigma by K. This K is the dielectric constant or relative permittivity. So what we can write, E is equal to sigma by K. Now you can write the equation for capacitance. C is equal to Q by V. Q by V. What is V? V is E into D. D is the distance between the plates. But now we found E as sigma by K. So we can write C is equal to Q divided by, what is E? Sigma by K into D. Q is sigma A. So sigma minus sigma P is sigma by K. So E was epsilon, sigma by epsilon 0 into K. So here there was an epsilon 0, I missed it. Okay. So sigma by, so sigma you can cancel there. So what you are getting? Epsilon 0 D by K. So you are getting epsilon 0 this equation was there. So we can write C is equal to Q by V. C is equal to sigma A divided by, what was C? Sigma by epsilon 0 K into D. Sigma you cancel. So you get epsilon 0 A by D into K. But sigma by epsilon 0 A by D, this was the capacitance without dielectric. This you write as C0. So what you are getting? C is equal to K C0. C by C0 equals K. So what will happen if a dielectric slab is filled between the space of the capacitor? Capacitance increases by K times. So on introducing a dielectric slab, between the plates, capacitance increases by K times. Okay. Now we can find the equation for the energy stored in a parallel plate capacitor. So if we introduce a dielectric slab between the plates of the capacitor, what will happen to its capacitance? Capacitance will increase. What will happen to the electric field between the plates? It will decrease, because you know E equals E0 minus EP. What is EP? Electric field due to polarization. Now we can derive equation for the energy stored in a parallel plate capacitor. Energy stored in a parallel plate capacitor. Okay. So you imagine a parallel plate capacitor. V is the potential difference between its plates. You know the meaning of potential difference? Work done to deposit a charge dq, or work done to transfer a charge, 1 coulomb charge between the plates. That is known as potential difference. Work done to move, to transfer 1 coulomb charge from one plate to another plate. That is known as potential difference between the plates. Suppose we move dq amount of charge, dq coulomb of charge between the plates. What will be the work done? Work done to move 1 coulomb charge is V. So work done to move dq charge is V dq. Work done to move dq charge between the plates is, what is the work done? dw equals V dq. And you know the equation. What is Q? Q is CV. So V can be written as Q by C. So dw equals Q by C dq. This is the amount of work done to move dq amount of charge between the plates. So what will be the work done to move a charge q between the plates? You have to integrate it. So work done to increase the charge. From 0 to Q coulomb. How will you find out total work done? You have to integrate the above equation. Integral dW. You have to put limit. You are increasing from 0 to Q. Integral Q by C dQ. Integral dW is W, right? You take C 1 by C common. Integral 0 to Q, Q dQ. You know the integral formula. Integral x dx is x square by 2. So W will be 1 by C into Q square by 2. W is Q square by 2C. This work done is stored as the electrostatic potential energy. Okay. So this is the energy stored between the plates of the parallel plate capacitor. This work done is stored as electrostatic potential energy. Okay. This work done, potential energy, we denote by the letter U. It is in an electric field, you write subscript E also. Q square by 2C. Also, you can write Q as CV. So this equation again can be written as energy is C square V square by 2C. So half CV square. So there are two equations for energy. Depending on the given quantities, you have to use the equation. UE is equal to Q square by 2C and UE is equal to half CV square. Okay. Again, you can write UE as half CV into V. So half Q into V. So we can express this energy in these three forms. This equation in three forms. So what is the equation for energy stored in a parallel plate capacitor? Half CV square or Q square by 2C or half Q into V. Depending on the given quantities, choose the equation. Okay. Then we will find out energy density in a parallel plate capacitor. Density in a parallel plate capacitor. Energy density in a parallel plate capacitor. Energy density is the energy per unit volume. Between the parallel plate capacitor, there is a space. So energy stored per unit volume in that space is known as energy density. So how will you find out energy density? Density, energy by volume. This is the parallel plate capacitor. This is the D distance. If A is the plate area, so what will be the volume of this space? This space is cylindrical. So base area into height, that equation we can use. So volume of the space. So volume of the space between the plates. What is the equation? Base area into height. Height is D, base area is A. So what is energy density? Energy, you know, energy stored in the capacitor, just we learned a previous equation, half CV square divided by A into D. And you know, for a parallel plate capacitor, C is epsilon 0 A by D. So what is energy density? Half C is what? Epsilon 0 A by D divided by AD into V square. You can cut this area, you can cancel. Remaining quantity half epsilon 0 V square by D square. And you know, V by D, you know, equation for electric field, E equals dV by dr, E equals V by R. So V by D is potential by distance, that will be electric field. So we can write half epsilon 0 E square. This is the equation for energy density in a parallel plate capacitor. Energy density in a parallel plate capacitor. Half epsilon 0 E square. Okay, children. That's the end of today's class. Thank you for watching. We will see in the next class. Goodbye.